If I thought that long-haired students tend to do badly in my exam and they are not smart, and if I say a huge number of long-haired students who are getting A pluses, despite my trying to stop them, if I don't change my prejudice, then I'm not open-minded. If I'm a Bayesian, what is the necessary condition that for me to be open-minded? I shouldn't assume that the probability that long-haired people can get A plus is 0. I can assume it's 10 power minus 158, completely fine. Long-haired people are not good. So the point is, as long as it's not 0, evidence can change your mind. So you're open-minded. Do you understand what I'm saying? So zeros are forever. You don't want zeros. Okay? Especially because you don't know that the data that you currently have, whether the data is complete or not. So one idea is you don't want zeros. How do you stop zeros from coming into fractions? Add a little to the top, add a little to the bottom. You see what I'm saying? And that's like a seeding. Like we give you like 2 points just for showing up to the exam. You see what I'm saying? Okay? That is seeding. And it looks like a completely dumb idea. You're just doing it to stop the zeros. But A, I'll tell you first of all that it makes sense. And B, I'll tell you that that's actually the right thing to do once you realize that you should have been doing Bayesian learning. And you decided to do MLE. And putting this little extra to the top and the bottom is your way of repenting for your sin of not doing Bayesian learning. I told you Bayesian learning is important. Not because you get to do it every day, but because it will tell you why all these crazy things are done to machine learning algorithms. Okay? So anyway, this idea is called, so basically this is called Laplacian smoothing. Again, one more beautiful word, Laplacian smoothing. What Laplacian smoothing says is essentially don't take any probability to be 0. Just give it, seed the probability, the numerator and denominator with a little virtual counts. And the idea is these virtual counts will eventually be overridden by the data if the data is large. Do you see what I'm saying? It will be overridden by the data if the data is large. But when the data is not large, it stops you from having zeros in the sequence. Okay? So by the way, so in fact, this is the point I made about having open mind is having the ability to change your mind, and which is equal to not associating a probability 0 to the event to begin with. Is a very, very important thing. This is basically Cromwell, it's also called Cromwell's rule. And Cromwell essentially told to the Synod of the Church of Scotland, I beseech you, in the powers of the Christ, think it possible, you may be mistaken. I may be mistaken that long-haired people are all down. So I think it's kind of true, so I'll put 10 power minus 157. But I won't put a 0. If I put a 0, that means I have metaphysical certainty. And so I'll never change my mind. Okay, yes?
So does this mean that probabilities won't add up to 1?
No, of course not. You'll see in a minute. It would be completely probabilities will add up to 1 in a minute. Okay, so in a way, what is happening essentially is that without that, you will see that essentially what this little trick is doing, this Laplacian smoothing is doing, is to capture some of what you lost by not doing Bayesian learning. And a way of actually thinking of Laplacian smoothing is act as if before. So here is the example. So this is the coin example again. So I just tossed a coin in front of you twice. Okay? It came heads both times. What's the probability that the third time I toss the coin, it will come again heads? You don't know which coin I'm tossing. No, I just tossed a coin heads. What does MLE say? Now the next time it will come heads. So it came tails, so the next time coming heads is 0. That's what you will say. Okay? But are you comfortable with that? Keep that in mind. Now, the same time, again I'll do a different experiment. Again, I take a coin from this side. I toss it 3,000 times in front of you. It comes heads 3,000 times. Now I'm about to toss it. What's the probability that it will come tails? 0. Are you more comfortable with this versus this? That's what Bayesian learning is capturing. If you had more data, so if I did see 3,000 tosses and it's still only coming heads, then I assume my prior expectation that coins are failed is completely out the window. Whereas here, I basically have to depend on my prior expectation. The reason whoever said it will still be 0.5 or something is because they thought it's still a normal coin that I picked up. Do you understand what I'm saying? And that's like saying I did not fall off a turnip truck. I was around. I've seen coin tosses before. And I have some idea about what's the prior on heads and tails for normal coins. You can convince me that I'm wrong by showing me lots and lots of data. This is exactly what I said in the beginning of the semester. I'll assume all of you are honest until you carefully convince me that you are not. You understand what I'm saying? So, and then you give me enough data, you will convince me the other way around. Okay? So that's basically what is happening. So the idea would then be that you can think of this as, act as if you have a bunch of virtual examples that you have seen in addition to the examples that are there. And say, let's say in this particular case, in addition to, for example, I'm trying to compute the probability that attribute I will have value j given the class variable I to be true. Okay? That would be written as essentially the number of the examples where class is true and attribute I has value, the required value, and normally divided by the number of examples where the class variable is true. This is what you would have done. The red stuff is what you would have done normally. Now what you do is you act as if there were m additional virtual samples you have seen before. That's why it's called m estimates. So you add, if you have seen m virtual samples you have seen before for the particular class, then I can add m here, and then I had here, of those samples, how many of them do you think will actually would have had attribute AI to be VI? That I will just, if I basically think that the attribute has 5 values, I'll assume 1/5 probability that you take any one of those values. So the P would be 1/5, so n times P is added to the top. You see what I'm saying? You do this to all the conditional probabilities. Okay? And the answer to your question is actually quite deep, which is the issue of, this actually goes back to previously as asked, is there a way I can put numbers in CPTs for this network such that the probability theory blows up? I asked this question multiple times in the class. The answer is no. You can put any old numbers as long as they're between 0 and 1, and it will be a probability distribution. Do you see what I'm saying? So that's basically the reason why the smoothing doesn't change anything. Okay, so this is called Laplacian smoothing, and if you understand what's going on, essentially Laplacian smoothing is trying to get you towards the Bayesian learning idea. And this is sort of done. Okay, you should be able to understand this. Okay, and of course, again, by the way, the other thing that all the implementations of any of these Naive-Bayes classifiers do is to think in terms of logarithms rather than in terms of multipliers, because if you do multiplications, because much of what happens in Bayesian estimates, the Naive-Bayes estimates, is multiplying a huge number of conditional probabilities. That will give you underflow errors. So you take logs. That's just engineering, just so that you won't get in trouble. Okay? The other very interesting thing is, why does actually Naive-Bayes classifier work? The quick solution, quick answer, in fact you can look at this later, is that in fact Naive-Bayes classifier would be pretty bad in approximating the real distribution function. but it might still approximate the relative ordering correctly. Okay? So imagine, given the evidence, the true probability that the class is true is 0.97, and the true probability that the class will be false is 0.03. Suppose your 9-Bayes classifier says the actual probabilities that the probabilities it computed are 0.51 and 0.49. 0.51, 0.49 are so different from 0.97, 0.03. But if you are into just picking the winner, the way we pick presidents, the same answer. You understand what I'm saying? And it's actually a very surprising thing. So Pedro Domingos wrote this paper that's cited heavily as showing that more often than not, although the distributions are quite inapproximate, the relative ordering is right, which gets us to the true-false questions and the gender differences. So in the true-false questions, typically people will have to guess either true or false. People should not be guessing here. The truly wise ones, wise men and wise women, know the answer. They'll write it. The rest of the people in this class will toss a coin and write the answer. Because maybe they toss a biased coin. So they might think, kind of think, sort of true. Okay. At that point, it becomes a question of false confidence. Okay. So sociological studies actually have shown that when there is negative marking involved, it hurts women. I'm very sorry to say this. Because apparently women actually say, if it is 0.51 and 0.49 according to you, you are not ready to say 0.51 wins the day. Whereas men have a lot more false confidence, according to these studies. I'm not one of them maybe. But, and then they'll say, oh, 0.501, 0.499, wow, 0.501 wins completely. So, full-on confidence. You see what I'm saying? And so, it's a beautiful study. I'll send you links to this, that in some sense, whether or not people, eventually you're converting probabilities into winners. Really, you should not convert probabilities into winners. The probabilities are probabilities. But, some of you try this, by the way. When we are doing the exam correction, I think my students come and say, this guy wrote this T with a little f and a V. So it's like a PF distribution. Unfortunately, we can't give any marks for that. Right? Okay? So that's basically, again, it's, this business of jumping to the conclusions after the probability is one reason why 9-Bayes classifier seems to work better than we actually expected. Okay. Now, structure and topology learning, which is probably the only thing that I'll be able to complete here because of the time limitation. So, structure and topology, one idea is just, if I don't know the topology, I'll assume 9-Bayes topology. Okay? That we have done already. The second is actually try on different topologies and see which one is better. That looks like a great idea. So you basically have five variables, let's say. You consider all possible graphs, all possible directed graphs on them, and try to search in them. So it's a beautiful thing where the number of graph configurations are discrete. The number of conditional probability values are infinite, they're continuous. So topology learning combines discrete and continuous search. Okay? And again, there's just too many topologies, so mostly people try to solve this by doing local search. Start with the topology, look for a better topology. So here is a simple idea. Suppose I give you two topologies. You can fit both topology to the data you have using MLE estimate, and then having fit it, you can actually compute the likelihood that these two topologies are given to the data. right? Because you're using the likelihood to compute the probabilities, and then you can also see how likely did they make the data. And the idea would be to pick the topology that makes the data more likely. Just like previously we picked the probability that will make the data more likely. Looks great, but doesn't work. Why doesn't it work? It turns out that if you have this network and this network, both are being fit to the same number of Perl examples, and you compute the probability, the CPTs for each of these, the best CPTs according to MLE for each of these, and using them decide how much of a likelihood they are giving to the Perl examples. It will always be the case that this guy gives more likelihood or equal likelihood than this guy. Because this guy has a superset of edges than this guy. Is this mind-blowing for you guys? Everything is mind-blowing. But suppose I have a bunch of points. I say fit the best line, and then after fitting the line, see the discrepancy of the points from the line. Then fit the best 17th order polynomial, and after fitting the best 17th order polynomial, see the discrepancy between the points from the polynomial. Which discrepancy will be lower? That's the same thing that's happening there. You see what I'm saying? In general, this is another way of saying you can never go wrong by being paranoid. Life would be inefficient by being paranoid. But you can't go wrong by being paranoid and assuming everything is connected to everything. Because then you will always say, yeah, whatever happened, I think it could happen. Everything is possible. Right? For example, the pizza guy probably happened. According to a complete network, anything can happen. You understand what I'm saying? So, given this, it's not enough just to say, compare the more network, more edges to the small edges. How did we get out of the problem here? You consider the complexity of the hypothesis. You basically say, in addition to lines versus polynomials, you know that if you keep on increasing the degree of the polynomial, the higher the degree, the more the training data error will be zero. Basically, this is training data error. That's what I'm talking about. Likelihood is training data error. Okay, so you can't just go with the training data error. Instead, you want to take into account some notion of complexity of the hypothesis. You see what I'm saying? So here you will then have to give some kind of a complexity of the network that's proportional to the number of edges in the network. That will then make you see what is the simplest network that also has the highest likelihood. So in a sense, you're doing loss function, which is likelihood, so the likelihood function, which is likelihood, plus a regularization term. What is a regularization term? That tells you a prior on the hypothesis. You actually think certain kinds of networks are more likely than others. And you had a prior. When you were in the heaven of Bayesian learning, you would have used it. Because you fell down to earth, you are trying to do MLE. And then you remember, I used to be in the heaven. I need to put some, basically this becomes a map estimation. MLE by itself won't work. You have to add map. The map part will essentially give the complexity of the hypothesis added to the likelihood. And then you maximize it. You see what I'm saying? That's how you do topology maximization, topology learning. Okay. Now, when machine learning algorithms say we learned the Bayes network underlying the data, this is what they're doing. If they then come up with some network, some random network like this, are you supposed to assume that the arrows are in the right directions? It must be causality. Now that you know how the sausage is made, you should never eat sausage. You understand what I'm saying? So you know that nobody really did any causality experiments in deciding how many edges to put. They just were just looking at some arbitrary maximization of the likelihood plus the simplicity of the network. So how dare you think that because there is an error, there's a edge, it is causal. So if anybody else does that, slap them. Okay? Certainly slap yourself if you ever do. That's it. Okay, so that's about that. There's 5 minutes, so I can do 8 more ideas. Let me do this actually, at least give you an idea, and then so that we can look at it later. So this is for the incomplete data. It's really truly mind-blowing. Everything is mind-blowing, but this is certainly mind-blowing. So I'm going back to my Russell example. Okay, I have this. I have the labels, and I have the examples and labels, and that basically can learn an I-based classifier. I learned one. I'm ready to use it to start predicting the test data. Then your friend comes running to you and say, hey, I found some more examples where Russell was loitering around restaurants. But because I didn't want to stalk him too much, I didn't actually see whether he waited or not waited. Do you understand what I'm saying? So I have some more examples whose label is not known. Would you like them? Can you use them to improve your learning? No. No, right? How many people think no? How many people think yes? Okay. That gets us, as this class does, to why are there, remember the math textbooks that you used to have in the high school? You know, remember in the high school you used to be kind of numbered, so you needed lots of examples. Lots of examples. So the math textbooks will have huge number of exercises. Right? Since you are undergrads and grads, we know that just one example or even lack of one example makes you understand. That's why I don't give you too many examples. But remember that in the math text there used to be all these examples, all these exercises. Remember that? But they would only give answers to the even numbered problems. What the? Why did they make problems for which there is no answers? Who are they trying to impress? Do you think those problems should have been removed from the textbook? Because the people who have done the problems with the answers and used that knowledge to do also the problems without answers, even though they don't know whether or not they were right, they are the smart ones. I hope some of you are here. The others who say it's enough to just go with the problems without the answers because you can copy the answer right away into the, into the homework. Those I hope are not here. Okay? My point is, unlabeled examples are like unanswered math problems in the math textbook. They're not junk. Okay? So, this actually can be useful. If the action that was useful then, it should be useful here too. How can I use it? First of all, you realize that when I get here, I'm talking about incomplete data. Right? Because this part is complete data, this is incomplete. Because it is consistently missing some of the values for the class variable. So, I will then tell you some magic idea. The magic idea is the following. You have this stuff, right? Use the Naive-Bayes classifier. Learn the Naive-Bayes classifier on this. Now that you have the Naive-Bayes classifier, you can predict the class for these guys. Yes? Now that you predict the class for these guys, all of a sudden you have 24 examples with labels. You see what I'm saying? Then learn the Naive-Bayes classifier on 24 examples. At this point, you relabel everything and then learn one more Naive-Bayes classifier. You do this for a while. until, for example, the likelihood of the data stops decreasing. You would have learned a better Naive-Bayes classifier. Crazy enough that that's just true. I'll show you some example here. So this is the guys who said, I don't need unlabeled examples, I'm never going to use them. These are the guys who said, I will take the unlabeled examples and I'll do that deal, which is essentially learn the Naive-Bayes classifier on the labeled examples. Learning part, learn the Naive-Bayes classifier on the labeled examples, then predict the labels for the unlabeled examples using this currently learned hypothesis. And in fact, when you predict it, one of the interesting things you have to do actually is notice that these are all yes, no, etc. But when you predicted this guy using, let's say, your first Naive-Bayes classifier, it might say yes with 0.7, no with 0.3. I will act as if these are fractional examples, just like in the likelihood sampling. Okay? If I do that, then the numerator and denominator will be decimal numbers. But thankfully, you know fractions even with decimal numbers on the numerator and denominator. So you can still do Naive-Bayes classifier. You guys see this? Okay? If I do that idea, and if I, for example, in this particular case, was given the same amount of training data for this learner as well as this other learner is using, there's extra 10,000 unlabeled examples that are sitting around. This extra learner is using these other 10,000 examples and doing this extra learning. When you are watching movies, some bozos who are doing the exercises without answers. And those are unfortunately the ones who do well in the exams. Not surprisingly, that's exactly what happened. Now notice that this is accuracy, learning accuracy. Now notice that as the number of training examples increases, you basically don't expect them to still diverge. Eventually, if there is a math problem, math textbook with 1 million even numbered examples, exercises for which there are answers, and they're also ready to give you another 1 million odd numbered examples, you say, heck with it. If you do 1 million, the ones for which there are answers, you will still do just quite well. Again, for the small training data problem, unlabeled samples can be used this way. Now, you don't have to think about this in terms of Russell example. You can think of this in terms of, I trained my classifier, since all of you guys like images, to recognize dogs, cats, whatever the heck is in the ImageNet, using the 14 million ImageNet labeled samples. But after a while, Fei-Fei Li lost her interest. She's no longer sitting there labeling every random picture saying, hey cat, hey dog, hey whatever. But people didn't stop taking pictures. There are even more and more pictures that are on the web. Nobody tells you whether they are cats or dogs. There are 2 points here. Point 1, actually you can use this idea. This unlabeled data of dogs and cats, blah, 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 the distribution, can be used along with the labeled data. And this idea is basically, you can call this semi-supervised learning. Semi-supervised learning. And semi-supervised learning is a general idea where you are giving some number of labeled samples and some number of unlabeled samples. And semi-supervised learning being done in the context of probabilistic graphical models is essentially the beautiful idea called EM, expectation maximization. What is the expectation? What is the maximization? When you learned a Naive-Bayes classifier from the data, you are maximizing the likelihood. That's the maximization step. Once I got that maximization, I got an NBC, which then I use to expect the labels for the things that don't have labels. So maximization, expectation, then again maximization on the whole data, expectation again. This is expectation, maximization algorithm. Okay? So by the way, the second thing is unlabeled data is a huge problem in general. So when people are saying AI is removing jobs, none of you have jobs, there are still jobs for people to look at pictures and say, this is a dog, this is a cat. And you get, I think, 10 power minus 17 cents or so per each picture. Which is enough that if you work for 3-5 months, you can buy like a Russian hamburger. Okay? But those kinds of jobs are all over the place. How many of you have heard of Crowdflower? Crowdflower basically is this company which does exactly that's all. So adding labels by humans for some particular area and then using them. But my basic point is that even if you don't have labels, you will be able to actually use them together. And this is expectation maximization. And one of the interesting things in expectation maximization, which I won't go into now, is that actually there are two things. Okay? One is, those of you who know hidden Markov models, in the case of hidden Markov models, the data will never tell you the state values, they'll only tell you the observation values. So it is a incomplete data problem. You know the topology, but the data is incomplete. So you use EM. The EM applied to HMM is called Baum-Welch algorithm. Here is something more directly relevant to your life. It's clear by now that there are grad students and undergrad students in this class. And there is conspiracy theory, I'm sure, that's floating in people's minds that this other group must be driving up the average. Right? It's pretty obvious. You need to prove it. How do you prove it? I normally give you just one nice normal distribution for the entire class. You want to argue that clearly there are two separate normal distributions. There's an undergraduate mean, there's a graduate mean. And please help me, whichever side you are on. The other side is the bad side. Right? So it turns out that that is basically saying there is a network, grad or undergrad, causes the marks. To give this network complete data, I have to tell you the grad student, their marks. The undergrad students, their marks. But all you get to see is just marks, which you will see by the way. But not know whether the grad students or undergrad students. So at that point, you can very quickly do EM. Assume the number of, basically this is a hidden variable. And you do essentially expectation maximization. And then you fit essentially a mixture of Gaussians for this problem. And that's how you then come and prove raw, clearly see. I know you know it, but we also know it. That this other group, the bad group, is driving up the average, and you can't fail us. Okay? So useful stuff you should do. And the last thing I want to say about this before we go into the ending part is, in the case of EM, the likelihood actually winds up being non-convex. So what really should be happening in EM is some kind of a gradient descent. And what EM actually does is, if this is the likelihood, it kinds of computes a lower bound